All right, this lesson is going to be about exploring and graphing systems of linear inequalities. This is section 6.2 and 6.3 in your textbook. So our goal in this lesson is to explore and solve situations that can be modeled by systems of two linear inequalities in two variables. So first of all, we'll define a system of linear inequalities. So a system of linear inequalities is a set of two or more linear inequalities. So that's important. So two or more that are graphed on the same coordinate plane. So however many inequalities we have, we would graph them on the same plane, and that would be considered a system. Now, how do we find the solution set for the system? Well, we look for the intersection of their solution regions, okay, and that represents the solution set for the system. And as we go through our look at Desmos and graphing, you'll see quite quickly how this works. So we'll start with a practice here. We got some pretty simple inequalities. We got 4 of them, but you can tell they're all single variable inequalities. So on the same coordinate plane, we're going to sketch the following inequalities and state a possible solution from the set. Now remember, the possible solution will be in the intersection of their solution regions. Always be aware if there's any restrictions on the domain and range. If there are none explicitly stated, assume x and y are elements of real numbers and therefore a continuous solution set. If there is a restriction to the integer numbers or the natural numbers or the whole numbers, it will be stated. And then you would have your discrete solution set. So we don't see any restrictions in terms of this number set, so we'll assume reals and thus continuous. All right, so we'll open up Desmos and we'll begin. So our first inequality is x less than or equal to 5. So we would plot that, type that right into row 1, x less than or equal to 5. The second inequality goes on the second row, x greater than or equal to -2, x greater than or equal to -2. On the third row, goes our third inequality, y less than or equal to 3. So y less than or equal to 3. And on our fourth row, our last inequality, y greater than or equal to -1. Y greater than or equal to -1. So again, when you have multiple graphs in Desmos, we can click on the circle on the left to mute all of them. So just a quick review. Remember, when it's greater than or less than, you have a dotted line. The boundary line is dotted, which means it does not include that value. So x would not include 5. It would be less than 5, non-inclusive. If we look at the second one, x greater than or equal to -2, solid line, and all values -2 or bigger would be inclusive in the solution set. Y less than or equal to 3, solid line, and 3 below for the y values would satisfy, and y greater than or equal to -1, anything for the y value that's -1 or bigger. All right, so now I will show you how we will put all 4 on the same plane. So first thing I'd like you to do is make sure that all 4 inequalities are going to be shaded the same color. So if you take your cursor and you look at the little gear wheel, that's edit list, you'd click on it. And what you can do then is go back onto the left, click on that circle, and you can select the color. So for this lesson, I'll click red. So I'm going to make them all red. So they're all the same color. So now when we click on them, I guess you should click done. When we click on them, you will see that they are all red. So we look for the intersection of their shaded area. So it is easy to find on Desmos when it's all in the same color. It's the darkest shaded area. So it looks like it's this rectangle here that's shaded. Now what we'll do is we'll click on the boundary points. So these vertex points, vertices or corners of a shape, we'll click on that first one, we'll click on the one on the right, the one below, and the one on the bottom left. So this rectangle would be considered all of the, sorry, everything within those 4 points would be the solution set. We do not look above, below, to the right, or to the left. If you were doing this on paper, I would expect that you would actually highlight that rectangular shape, but we're doing this in Desmos, and that will be fine just to actually take a snip of this graph and put it into our Word document. So I'm just going to review that. We will snip in a second. So got the 4 corner points. I think I'm zoomed in enough. It's good. So just a review on snipping. Remember, you would type in on your search on the computer, snip tool. There we go. It comes up. And we'll do a new snip. Please move it off to the left or the bottom, and we'll crop the picture. So there is our graph. We'll right click copy. We'll go to our notes and we will put it in there. Control paste. It's really big right now, so we will just make it smaller. And there is our graph. So we have our system of linear inequalities. We have all four of them graphed, and we have clearly the solution region. So to state a possible solution from the set, what we can do is pick any intersection point, so any coordinate pair. So for example, if I go back to Desmos, 0, 3 would fit. This is x, so 0 is greater than 5. 0 is less than or equal to -2. Is greater than or equal to -2. 3 for the y. 3 is less than or equal to 3. And 3 is greater than or equal to -1. For example, if I tried the 0.50, whoops, we'll just zoom out. If I had the 0.50, well, sorry, that point would be 0.5. 5 doesn't work because 5 is not less than 5. So therefore it wouldn't satisfy. So any points outside of this shaded region would not satisfy the inequality. So if we were going to state a possible solution, one possible solution, and we would state it as a coordinate pair. I'll again pick the point here, which was 0, 3. So 0, 3 is one solution, or you could state it as x equals 0, y equals 3. Okay, more commonly to present it as a coordinate pair, but that's fine. Okay, so that is how we do inequalities, systems of inequalities on one coordinate plane. So now let's move to the next step, which is looking at 2 variable inequalities. So again, it's going to be pretty much the same idea. First of all, we look at the inequalities. Notice here we have the greater than symbol, not inclusive, so it means we'd be expected to see a dotted line on the boundary. Here we have greater than or equal, less than or equal to, which means a solid boundary and thus inclusive of the boundary. There are no restrictions stated, so we're going to assume x is an element of real numbers and y is an element of real numbers, and thus we will have a continuous solution set. So we'll go back to Desmos. We will clear what we've done and start from scratch. So to save time, I'm just going to copy paste over, but you could type them in, but I will just copy paste. So there's our first inequality, and there is our second inequality. And again, we want to make them the same color. So we'll go to the gear wheel, click on, I'll make them red again. Let's make them orange just for fun. So I'll make them orange, done. And now you can see where the solution set is. So if we zoom out, you can see here that this is the overlap. So it's above the dotted, it's above the first inequality and it's above the second. So it's kind of that shape. If I zoom out, you can kind of see what it would look like. So hopefully that makes sense to you, that this up here would be the shaded area, an intersection of the two inequality shaded areas, and thus the solution region for our system. So just going to zoom back in. There we go. And sorry, zoom out 10. All right. So we got the graph. We're going to get the graph into our Microsoft Word. So again, snip, new snip. And again, I want to, because it is going into quadrant 2 and in quadrant 1, I want both. So I will snip like that. Right click, copy into our Word document, Control V, and again, make it a bit smaller, and we've got it. Okay, so now we have our graph, and it says state a possible solution from the set. So again, we're looking for everything, okay, in here. Everything that's in the intersection region, so not below the dotted line or not to the right-hand side of the second inequality. It has to be in between. So again, it says just state a possible. It means that there's more than one. So let's state two possible solutions. So first possible solution. You can look for a different one at home, but I'm going to pick the point x is equal to 1, 2. So x is 2, and y is equal to 2. So 2, 2 fits. And how do we know? It's in the solution region. Second possible solution, I'll just show that this is continuous. So we could go x equals 1, we'll go 2.5. So x equals 2.5. And we'll go up, so 1, 2.5, and we'll go up 1, 2, 3, 4, 5.3. Okay, so that point right there is in between. So 5.3, that is a second possible solution. So I'm sure you could imagine you could find all kinds of solutions. So those are two examples. So hopefully you now see how we graph a system of linear inequalities through Desmos and putting it into a Word document to show our graph. So now, further your understanding, I would leave this to you for homework. 3 systems of linear inequalities have been graphed. For each system, describe what you can infer from the graph about the restrictions on the domain and range. Actually, we'll go through this. So you can see we have A, B, and C. All right, the graphs look different. In class before, we were talking about stippling for a discrete solution set. Here, there's no stippling. This is continuous. So we would assume that there's no restrictions. Okay, X can be in quadrant 2 or 1, and Y can be in quadrant 4 or 1. And there can be in between numbers, so reals, so there's no restrictions. But if we take a look over here, all right, you'll notice that we've got these green dots at the intersection point. This is telling us that X and Y must be discrete. Now, because we have X and Y into the negatives, it's most likely that the restriction here would be X and Y are integers. Okay, because it goes into the negative. If you look on the third one, you'll notice that we have Y shaded or dotted again below the negatives. So that looks like integers as well. And X is also in the negatives. And it's stippled, so that tells us that it could be integers as well. So X, actually my apologies, that's the boundary line. We look for the shaded region. So Y must be above 0, which is whole numbers, but X is negative here and positive here. So X, X is all whole numbers, sorry, all integers. Y is all whole numbers. I'm writing this in words. I'm not doing the set, like I'm not using the set symbols just for this. So you can go X, E, I, and Y, E, W if you wanted for the set notation. As you see here, X, E, R, Y, E, R. So I'll leave this one for you, number 2, to practice graphing. I'd like you to graph this Desmos and locate 2 possible solution sets. So I'll just write it here, graph and state 2 possible. Okay, so that is an overview of graphing systems of linear inequalities. So let's put it into context here. So we are going to look at an example of putting systems of linear inequalities into context. So we are going to try to solve a problem that's going to essentially help a company that makes boats decide how many aluminum boats and how many fiberglass boats they should make per day. And this is a linear inequality scenario. And if you were the owner of this company, instead of guess and checking how many boats you should make each day, because obviously you have to pay workers to build the boats, you have to buy the supplies, you would want to use some math to help solve a real problem, which would be to make the optimal number of boats to maximize your revenue. So let's take a look here. A company makes 2 types of boats on assembly lines: aluminum fishing boats and fiberglass bow riders. When both assembly lines are running at full capacity, a maximum of 24 boats can be made in a day. So that's important. That's telling us the maximum production capacity. The factory cannot make any more than 24 boats. The demand for fiberglass boats is greater than the demand for aluminum boats, so they need to make more fiberglass boats than aluminum boats. So the company makes at least 4 more fiberglass boats than aluminum boats each day. List 2 possible combinations of boats the company should make each day. So I will show you, we're going to go through this as to how we can use systems of linear inequalities to solve this question. And this is going to be setting us up for the next lesson, which is linear programming, finding optimal solutions to these different scenarios. So first things first, we have to assign variables. And it's clear we have 2 types of boats, aluminum and fiberglass. So aluminum, we're going to say is X, and fiberglass, we are going to say is Y. So I would state that right off the bat. So X is the number of aluminum boats made per day. Y would equal the number of fiberglass boats made per day. I guess changes to the American spelling because Microsoft Word likes that. All right, so we have X and Y. So that's the first thing. We're going to write out our variables. Next, it says write out domain. Write out the domain. That should say domain and range restrictions, as well as the equations to model the situation. So domain and range restrictions. This is basically telling us what quadrant are we going to hang out in. And I hope you would realize that if we're talking about making boats, you can't have negative boats, and you certainly can't make part of a boat. Well, you could, but you're not going to sell part of a boat. So we're going to assume that the number of boats made cannot be negative, nor in parts. So our restriction then would be X and Y are whole numbers. Okay, so X and Y are whole numbers. And how would we state that? X would have to be greater than or equal to 0. y would have to be greater than or equal to 0. And this makes the graph hang out in quadrant 1. Okay, so that's that. Next is the equations to model the situations. We're going to have two inequalities. So two inequalities model this situation. Our first inequality has to do with the maximum production. We'll say daily. The second one would be the demand for fiberglass boats. So essentially what we're going to do is build inequality number 1 for the maximum boat production and build inequality 2 for the demand for fiberglass boats, which will then give us a system of inequalities, which of course we can plug into Desmos and get our answer there. Okay. So our boat production, it says maximum boats, 24 boats can be made in one day. So if X is the number of aluminum boats and Y is the number of fiberglass boats, X plus Y, it would have to be less than or equal to, so we'll use the proper symbol here, less than or equal to 24. So they're saying that you can make a maximum number of 24. So if you make 20 aluminum boats, you can only make 4 fiberglass, and so on. Demand for fiberglass boats is greater than the demand for aluminum boats, so the company makes at least 4 more fiberglass boats than aluminum boats each day. So for example, if you make 1 aluminum boat, you must make 1 plus 4, which would be 5 fiberglass boats. So how do we build this inequality? That at least means there must be at least 4 more fiberglass boats than aluminum boats. So if X is our general number of aluminum boats, X, X, now 4 more then means plus 4. X plus 4 would have to be less than or equal to Y. So Y being the number of fiberglass boats, if you read it backwards, Y would be greater than or equal to X plus 4. So those are the two inequalities. Now we can graph them. Okay, so we'll see if we can copy paste this into Desmos to make our life a little bit quicker. We have to reset and it works. So X plus Y less than or equal to 24. And the second inequality. Okay, so zoom out there. There we go now. As you can see here, problem, we're not hanging out in quadrant 1. We're hanging out in all the quadrants. So we have to state our restrictions. So our first restriction was X must be the whole numbers. So X must be greater than 0. Nope. Pause on that. We are stating our restrictions. Pardon me, we've done this before. So remember, we go up in here, our set notation, we say X greater than or equal to 0. And then Y greater than or equal to 0. So my apologies there. So you actually have to set up both restrictions. So if we just quick lead back up, restrictions, X and Y both must be greater than 0 to be hanging out in quadrant 1. Make sure that you in Desmos include that restriction. So you just enter it as I just showed you. And if you have to save time, you can copy and then paste into the second. So now, as you can see, this graph is hanging out in quadrant 1. So if we want to be a bit more fancy here, we can go to graph settings and we can label our x-axis. X represents the number of aluminum boats produced daily, and Y is the number of fiberglass boats produced daily. Okay, so we now have our system of inequalities, and we are going to look for a solution region. So the solution region is the overlap. So if again we go press on the gear wheel and we'll make it red, now you can see clearly the solution region. So 0.25, 0.24, I apologize, 0.4, and this point here would be the maximum. So that point would be 10 and 14. So 10, 14 would be the maximum. So any combination of boats in here would satisfy the daily production requirements. So I want to get this into my Microsoft Word because I've done my graph. So again, we'll do another snip, new snip. I want to have all the titles there. So I'm going to be careful with my snipping tool. Yes, it's going to catch that. That's all right. So that's good enough. We have that. There's our graph. Looks great. Copy. Paste. And we don't need it that big, so we'll make it smaller. And there we go. So there's our system of inequalities graphed. The last step, I'll just bring this back up onto the single page. As you can see, where the two shaded areas overlap is your potential final answer. And we can state a final answer. So we just have to pick 2 points in the solution region. So I'm going to pick X is 5 and Y is 10. So I'm going to go point A, and we always label our points, capital letters, colon, and then state it as a coordinate pair. So X is 5, Y is 10. And second point B, we'll go X is 3, Y is 15. So the second point is 315. So what this tells us then, point A, we could produce 5 aluminum boats and 10 fiberglass boats. And for this point, we could produce 3 aluminum boats and 15 fiberglass boats. So here you can see that X is bigger than 0, Y is bigger than 0. 10 plus 5 is 15. 15 is less than 24, which was our constraint. And 10 is bigger than X. 10 is bigger than X plus 4. So 5 plus 4 is 9. 10 is bigger than 9. So that satisfies the demand. On the second point, X and Y, 3 and 15, are both bigger than 0. 15 plus 3 is 18. 18 is less than the maximum production, which is 24. And 15 is greater than 3 plus 4. 3 plus 4 is 7. 15 is greater than 7. So these would be 2 possible combinations of different of aluminum and fiberglass boats that this company could produce per day that would satisfy their constraints. We will be learning later on how to find what we call optimal solution. Okay, so here we might be talking about, well, what combination would make us the most money? So we want to find the maximum And if we wanted to find out which combination would cost the least to produce, then that would be a minimum answer. So we'll be talking about that in the next lesson when we talk about linear programming. So example 2, I'll leave with you for homework. You can try that. There's no context here, so it's again just practice graphing a system of inequalities and choosing 2 possible solutions. And for homework, you can try on page 318 and 319, numbers 4, A and B. There's no context. Question 10, question 11, and question 12. And if you have any questions, please email me. And that concludes our lesson on exploring and graphing systems of linear inequalities.